now. Today, our distinguished speaker is Professor Yuanhan Zhang Yuanhan from Academia Sinica. And about his education background, he got his bachelor degree in physics from National Taiwan University in 1983. I think that's exactly 10 years before I did. So, like my school brother, 10 years above. And then 7 years later, he got his PhD from MIT. And following that, he spent 4 years as a postdoc and then a researcher at MIT. So he returned back to Taiwan in 1994 to join the physics faculty at the National Central University. And currently, he is a distinguished research fellow at the Institute of Physics at the Academia Sinica. And his research field is mostly about the experimental particle physics, and he's particularly interested in the detector and instrumentation development for new physics. And Professor Zhang participated in several collider experiments, including the L3 Phobos and the CMS, and also a balloon experiment at NCT. And currently, he is a member of the MS experiment, which is a spaceborne detector on board of the International Space Station 国际太空站, measuring the fluxes of cosmic rays. And in 2019, he initiated a local dark matter experiment, TASEH, in National Central University. And his early career mostly focused on the measurement of electrons and muon-related standard model processes. And after joining the AMS in 1994, that's about the time he returned back to Taiwan, he did experiments, he did a measurement of antiparticles in cosmic rays, including the positron, the antiprotons, and the antideuteriums, to search for dark matter and the antimatter in the universe. And with the experiment TASEH, he looks for light axions dark matter with a detector whose sensitivity approaches the quantum limit. So I think today he will be spending some time sharing with us some quite interesting and also latest development of his recent work in the search for this mysterious dark matter in the universe, from the TeV energy scale to the mu EV. So let's welcome Professor Zhang Yuanhan.
Okay, thank you, Proti. Is this clear enough?
Yes, very good.
Thank you for the introduction. Let me start by saying that the title Search for Dark Matter from TeV to Micro-EV looks very exciting, but it's not continuously from TeV to Micro-EV. It's just I'm working on two experiments, one at TeV energy range and one in Micro-EV energy range. They are 18 orders of magnitude different, but both are very interesting. So let me first give you a very brief introduction of dark matter and the implications. I think many of you already know the existence of dark matter, and this famous pie chart shows the sharing of the energy in the universe. Dark energy takes about 70%, and the remaining is dominated at dark matter, 26.8%. The non-standard model particles takes only 4.9%. That is to say that at this moment, we actually understand only 5% of our universe. Now, of course, it is very interesting for us to if we can get some insight of what is the dark matter and what is the dark energy. So let's just focus on dark matter. The existence of dark matter is deduced from the gravitational effects, including rotational speed of stars around the galaxies, motions of galaxy clusters, gravitational lensing, CMB, cosmic microwave background, BAC, baryon acoustic oscillation, etc. Each of them at some point sees some anomaly, namely abnormal behavior. However, all these anomalies can be explained by a single assumption that there are some unseen dark matter. It turns out a lot of unseen dark matter. Cannot see them, so dark matter is non-baryonic, meaning it doesn't contain any quarks. In fact, also no electron, and it has to be charge zero. So because if they are baryonic or has charge, we would have been able to see them. Since we don't see them, they're non-baryonic, charge zero, and they are cold. By cold, I mean the particle is moving at the non-relativistic speed. How do we know that? We know by observation that the dark matter seem to stay around the galaxies. So which means that their speed is smaller than the escape velocity of galaxy, about a few hundred kilometers per second, or 10 to minus 3 speed of light. So these are what we mean by cold. We also expect that they are weakly coupled to standard model particles, very weakly. Now, let me give you a remark. I think the very last item, weakly coupled to standard model, is invented by there's no evidence, it's just invented by researchers like us, because you have to justify your work, and if the particle have no interaction with standard model particles at all, then we cannot search for it. There's no meaning doing any experiment. So we said just for us to be able to do experiments, this particle has to be weakly coupled to standard model particles. That's a joke, but I think that's what happens. So let me summarize. Dark matter is well established by gravitational effects in large scale, but so far there's no indication from laboratory experiments. No particle or phenomena with expected properties exist or has been observed. Theorists are always very capable, so they have already invented many possible models or theories that involve in new physics. And from all these published theoretical models, dark matter models are based on elementary particles are somehow favored, probably because it's more easily to construct a model this way. Now, what can we do to understand dark matter? In two ways. First, we look for particle based on certain model. Mostly we look from the collider experiment, for example. In collider, particle collides and create new particles, and we look for particle that with a property that is similar to what we expect from dark matter models. We can also look for some phenomena outside of gravitational effects induced by dark matter. This is so-called indirect search because we don't search for that particular particle directly, but look for some implications. So let me first say that in the Academia Sinica, we do have a quite wide range dark matter search program. Starting from LHC, we look for dark matter with TeV mass, TeV 10 to 12 electron volts mass particles from the LHC particle collision. And then we have AMS experiments looking for anomalies in cosmic ray antiparticle spectra, which is due to dark matter annihilation. This covers range from TeV to about 1 GeV mass range. And then there's a CDEX experiment, which is evolved from neutrino detection. They look for recoil particles from dark matter and matter collision from 10 GeV to about 1 eV range. And finally, this TASE experiment look for QCD action on dark matter with a haloscope type experiment. It's looking for dark matter at the tens of micro eV. So it's a wide range of math possibilities. And today I will report to you this AMS experiment and TASE experiment, which I have been involved. So let's start with the AMS. AMS experiment is a spaceborne detector. This is AMS. It now sits on the International Space Station. It's measuring the cosmic rays. So if we look at this picture, shows the cross section of AMS. AMS is a detector that composed of several sub-detectors. From top, we have a transition radiation detector, which identify electron and positron. And then there is a magnet, the orange part. It's a baromagnet, which provides a magnetic field together with the magnet and the 9 layers of silicon tracker, 1 to 9 layers of silicon tracker, which measures the bending of particles, the track of the particle, and the bending of the particle in the magnetic field tells us the momentum of the particle and charge of the particle. On top and bottom of the magnet, we have these green layers, 2 time-of-flight detector, which measure the speed of the particle in its direction. At the lower part, we have a ring image Cherenkov detector, which measures the speed by Cherenkov light. And finally, an electromagnetic calorimeter, which measures the energy of electron and positron. Now, with the reason that we need all these detectors is because we need measurement. We have to measure the momentum, the charge, the rigidity, the energy of the particle. Eventually, we will reconstruct the flux of the cosmic ray particles. By looking at the different responses of particles in different sub-detectors, we can identify what type of particle it is. For example, what you see in each detector for electron is different from that of proton. Note that the difference in ECAL, and different from that from iron, for example. So this we can identify particle. And very important, and actually the most important feature of AMS is that we can separate particle from antiparticle. This is because AMS is a magnetic spectrometer, and antiparticles bends in an opposite direction compared to its counterpart particle. So with this, we can identify antimatter particles. And this figure shows how well we can do that. The y-axis is the charge confusion fraction. That is the ratio of particles that we have identified the charge sign incorrectly. The x-axis is the energy of the particle. So up to 10 to 3 GeV, namely 1 TeV, we have only about 10% of charge confusion. And this established our capacity of measuring the antiparticle. If the energy is at 100 GeV, then the charge confusion is down to about 10 to minus 3. So how do we look for dark matter from this? We look for dark matter by, first of all, we have to have an assumption what is a dark matter. One of the leading candidates of dark matter is the WIMP, weakly interacting massive particles. This is a very general term, but one very solid example is supersymmetric neutral particles called neutralino. if neutrino is at about 100 GeV mass, they are produced thermally in the Big Bang, and the amount would be just about right to observe the dark matter density in the universe. So people used to call this a WIMP miracle, but I doubt it because we have never seen a neutrino in the laboratory. But in any case, that's one example of how this a dark matter particle can be created and how they can survive. This is a good model. So AMS look for if this kind of neutrino is the dark matter, then we are living in a universe surrounded by a lot of neutralinos, and neutralinos can interact by annihilate with each other. So neutralino annihilate, and they can create quarks and leptons. Finally, they will decay to become positron, electron, antiproton, or proton. And they are in the they are in everywhere. This happens everywhere in the universe, and therefore these particles will become cosmic rays that we detect. However, in the cosmic rays, there are a lot of electrons and protons. So the amount of electron and proton created by dark matter is not really visible. It's too small compared to the existing ones. However, cosmic ray positron and antiprotons are very rare. If there's an additional contribution from dark matter annihilation, we should be able to see them. That's how we want to measure the positron and antiproton to infer the existence of dark matter. So let me use this cartoon to emphasize this point. Normally, we know that the primary cosmic rays, proton, helium, and electrons, are produced in supernova explosion. They're accelerated to high energy and travel through the space as cosmic rays. These particles collide with interstellar medium and produce during the collision positrons, antiprotons, and antideutrons from collision. Now, in addition to this, other sources like astrophysical sources, pulsars, can create and accelerate positrons. As mentioned, annihilation of dark matter particles can also create positrons, antiprotons, and antideutrons. They all come around in the galaxy and measures together as the cosmic ray. So if we are able to measure precisely the spectrum of antiparticles in cosmic ray, we may be able to distinguish the source of the antiparticles and eventually infer the existence of dark matter. And so let me first come to the result of our measurement in positron and electron. What we expect from cosmic ray. Normally, cosmic ray are described very well by an initial rise and then a power law decrease as a function of energy. So the y-axis is the flux. In here, we multiply it by energy to a third so we can see it more clearly. But in any case, it's an increase first with energy and then decrease of power law. The initial increase is due to a solar wind, which blocks the low energy cosmic rays. So let's focus on the high energy part. The high energy part gives us the true nature of cosmic rays. Now, what we expect is a power law decrease. This is also seen in proton and helium and others. So electron seems to be in good agreement with other particles. But positron, on the other hand, the yellow point, shows a spectrum that looks very strange. It's flat first, and then it starts to increase up to about 300 GeV, it starts to decrease quickly. So if you are a particle physicist, you see this kind of strange bump or peak-like structure, you get very excited because this kind of structure normally means there are new physics in this particular energy scale. There must be something different that gives you this increase. So this is called the positron axis, and this has been observed in early 2000 years. And now for us to establish one important observation is that it starts to decrease at high energy. Although with large error bar, we are able to start to establish how real is it, this decrease. So what we do is we describe the cosmic ray spectrum, the positron spectrum, with this simple phenomenological model. Its first term described as rise due to solar wind, and then we describe a power law, which is describes the cosmic ray from collision. This is what we expect to have. And then this part, we use a power law function times exponential cutoff. This is exponential function which describes the fast drop at this scale. And this energy ES describes where the cutoff happens. By fitting, I think it's really pretty good fitting, and we have established that the cutoff energy is not infinity. That means we have seen the cutoff effect with 4.5 sigma of significance. So there is indeed something strange. It's a cutoff behavior. Now, of course, we can try to fit it with a more realistic model of cosmic rays with the dark matter. And here, this figure shows some effort from the theorist to fit the spectrum with contribution from cosmic ray collision. This is what we know and expected, and plus a contribution from dark matter. You see the fitting is even better. This part is a new source. So that's what we know from positron. And then let's look at the electron. So electron seem to have just a power law decrease, e to the minus something. But now with a smaller and smaller error bar, you can see that at high energy region, there seems to have some structure here, bumped structure. That's interesting. We don't see this before because when the error bar is big, this small structure doesn't show. But now, if you extrapolate, we do see this slight increase. This slight increase gives us some hint and tell us that it may be the same coming from positron. That is, if we describe this electron spectrum together with this term from positron measurement. Here, first we fit the electron spectrum by two power laws, power law A and power law B, plus a cutoff term, which the parameters are from positron measurement. And it can fit the data very well. And actually, this term is needed to fit the data with a 2 sigma significance. So we see that the electrons seem to also have a contribution from the same new source. We don't know what is this source, but it is a phenomenon that we have observed. Of course, there's one possibility that this source comes from pulsars. Pulsars produce and accelerate both positron and electron to high energy. However, pulsars do not produce antiproton, even though it's very high energetic. It's not energetic enough to create antiprotons or antideutrons. So this is a good indication. Let's look at the antiproton. This figure shows the antiproton spectrum in the blue point compared to that of positron, which we've already seen, but plotted in a different scale. Now, it's actually unexpected and very surprising that antiproton and positron seem to have the same spectrum shape, up to above 60 GeV, up to about 500 GeV. And if we take the ratio between positron and antiproton, we see that the ratio E plus to P bar flux ratio is at exactly 2 as a constant over a wide energy range. So it will be really interesting to know whether this is a pure coincidence or these are coming from the same source like dark matter. Of course, you can see that the most important thing is we want to collect more data so the error bar becomes smaller to be sure. So now we have seen the effect from electron, positron, and antiproton. What else can we do? Well, one thing we can do is if we can measure positron to higher energy, for example, up to 1.5 TeV, 1 exapoint, because if this is a cutoff behavior, there is a cutoff. Above that cutoff energy, there should be no effect. So this last measurement should return to what we expect without dark matter. So this last point is very critical for understanding of this interpretation of positron excess. So this is one thing we can do, but this we have to take more data. The other thing we can do is we look at the third antiparticle that's supposed to exist in the cosmic ray, the antideutrons. Antideutrons are charged -1 particle, but 2 times heavier than antiproton. Because of its mass, it has a very distinctively different production rate if it's from collision or if it's from dark matter annihilation. From collision, the production rate is showing this black curve. It's highly boosted because it's a high energy collision. Highly boosted tends to be at higher energy. For dark matter annihilation, in annihilation they are produced at rest, in the rest frame, so they tend to have lower energy. So it's a natural distinguish between dark matter model, the magenta color one, and the collision model for antideutron, if we measure it in the cosmic ray. So here we see the spectrum of mass spectrum of charge 1 particle measured by AMS. The yellow points are the measured result, the mass times sign of charge. So we see a peak of proton around 1 GeV, deuteron and antiproton from cosmic rays. We also see the peaks corresponds to pion and kaon, which are coming from proton interacting with the detector. Data in Monte Carlo agrees very well, and we see there are 70 million deuterons. And then on the other opposite side, in the anti-deuteron signal region, where the mass is 1.8 charge -1, we observe one event. This is in agreement with the background expectation from Monte Carlo. And I should mention first that this is for the beta velocity between 0.5 and 0.8 speed of light. So there's basically probably just a background event. Now for higher beta region, beta between 0.95, 0.98, we use ring image Cherenkov to measure the speed better. We see again a very good agreement between data in Monte Carlo and also the proton, deuteron, antiproton spectrum. This time we have 4.5 million deuterons and a few candidates anti-deuteron on the left-hand side. This candidate of anti-deuteron is still somewhat in agreement with the expectation for background, but still you see that the fluctuation is higher, larger due to less number of events. So we still have to expect to take more data to pin down the true nature of these events. But however, in any case, if we interpret this excess of events as a particle flux of antideutron, currently our measurement has already established that at the low beta region, antideutron flux is excluded above 10 to the minus 6. That is, antideutron flux is below 10 to the minus 6 in the unit of per meter square per second per steradian per GeV. At the higher velocity region, it's also excluded at about the same level. So this is the two region that we can establish our exclusion. Together with this exclusion plot, we show some model prediction with dark matter model in the yellow color, two different dark matter model, and from just without dark matter, just the collision contribution. And you can see that our current exclusion plot already has is already sensitive to some of the model. Now, AMS expect to run another 8 years up to 2030. So by that time, we expect our sensitivity will increase by 1 order of magnitude to about 10 to the minus 7. And hopefully at that time, we are sensitive to most of the antideutron models and really probe dark matter with antideutrons. So that's the story that we have about searching for dark matter in AMS. I have one comment about the lifetime of AMS. People question whether AMS can really work up to 2030 because it's already a quite old experiment. It has been working in space for 10 years. We used to worry about that. Major concern for AMS was that when there is a hardware failure, it will be extremely difficult to repair because it's in the space station and outside of the living quarter of for astronauts to repair it. They have to work with a spacesuit. That's very difficult. And then in that case, lifetime of AMS is limited by its weakest component. This situation actually became a reality when AMS tracker cooling system started to fail in 2014. The system has built-in 4 times redundancy, but they break at the rate of about 1 failure per 2 years. So we expect that everything will, the AMS will end after 8 years, due to mostly probably due to insufficient lubrication of CO2 pump. However, with the major effort from the engineers and with the help of NASA, a new system was designed and installed by astronauts with 4 spacewalks in 2018. This picture shows astronaut with the new pump system taking a spacewalk. So with this experience, AMS has demonstrated that upgrade and repairments are possible. So AMS lifetime, instead of limited by the weakest component, is limited only by the ISS lifetime, the space station's lifetime. Currently, it's 2030. And also, AMS now is planning an upgrade, adding 1 layer of tracker at the top of detector to increase the positron acceptance by a factor of 4. And that's how we hopefully will be able to improve our measurement precision and up to 1.5 TeV of positron energy. So this is the perspective of AMS running up to 2030 with 4 times acceptance. So we can stay tuned for any news. Now let me switch to the other extreme, search for action dark matter. So instead of very heavy dark matter, we are now looking for very light dark matter particle. This is called action. Action is a particle coming from consequence of so-called Patrick-Quinn symmetry or symmetry breaking of Patrick-Quinn symmetry. It's proposed to solve for another problem called strong CP problem. The strong CP problem means why strong interaction do not have CP violation. Now this proposal, this symmetry breaking solves the problem, but it also brings in a new particle called action. It's a pseudo-scalar particle, couples to standard model particle very weakly, and it is expected to produce with large quantity in the early universe. In terms of dark matter, if we put action in the picture, then action actually can serve as a good candidate of dark matter. It's very stable, it's non-baryonic, no charge, very weakly interacting with standard model particles. Now we believe it has very low mass. However, it is indeed cold by production. The production mechanism dictates the current temperature of the actions in the universe. So if we are able to find action as a dark matter, it solves two problems in one go with one particle, solve the problem of dark matter. It also solves the problem of strong CP problem. How do we detect action? Way to do it is through this interaction. Action can couple with photon by this effective Lagrangian, a coupling constant times action field times E dot B from the two photons. So it's on the Feynman diagram, the vertex shows as action coupled to two photons. This theory is quite interesting, quite simple, because it has only two parameters. One is the coupling constant, one is the mass of the action. This figure shows the action coupling constant versus mass. The yellow band is the prediction from QCD. There are some different theoretical models based on different implementation of action in QCD. So KS3Z is one benchmark model, DFSZ is another extreme model. Now, then the orange, blue, and green color region is what experimentally has excluded in the parameter space. The green colored one is so-called haloscope experiment, which is a narrow band search, but with high sensitivity. On the other hand, helioscope, the blue region, and the light through the wall, they are wide band search, but their sensitivity is much worse. The haloscope has very good sensitivity because we assume in haloscope experiment we assume that dark matter is made of actions. So nature provided with us with a huge amount of dark matter, just because it's the huge amount of actions, just because it's the dark matter, and that's why it can reach very high sensitivities. Okay, so this is the current status, and our experiment is in the haloscope type experiment. So how does it work? What do we mean by haloscope? Halo on one hand it means that dark matter is the halo of the galaxy, and it also means that it's sort of a very dense cloud surrounding us because of action is very light and number density become very high. So a very high density action flow can behave like classical waves going through us in Earth, in everywhere. Now, the way to detect it is if we have a very strong magnetic field. So action couples to two photons, and one photon comes from the magnetic field, and then it becomes action produce one photon. By energy conservation, this photon has energy corresponds to the mass of the action. So the frequency of the photon is equivalent to the mass of the action because it's cold. So here in the strong magnetic field, if we are looking at the picture with strong magnetic field, the flow of action may have a chance to convert into such a photon. Now, how do we catch this photon? Normally, such a photon comes very rarely, and we have to be able to catch it and so to measure it. So what we do is we put a cavity inside. If the resonance frequency of the cavity, the EM mode resonance frequency, is exactly the same as the photon's frequency, then this photon can stay in cavity long enough for it to be captured by the antenna and eventually to be digitized. So that's the basic story, but there's one other thing we have to pay attention to is that we know that there's a background radiation, the black body radiation, when there's a temperature. So in order to avoid a lot of photon from thermal radiation, the black body radiation, we have to put the whole apparatus in a very cold environment to suppress the background photon from thermal radiation. So these are the basic of a haloscope. How it works, this cartoon shows how we actually operate this experiment. Cavity in a magnetic field. If there's action comes in, it generates a resonance electric field oscillation in the cavity. So now, one thing you may question is that how do we know that the resonance frequency of cavity is exactly the same as that of the mass of the action? We don't know a priori what is the mass of action. So let's say, assume that the mass of action corresponds to a frequency here, and we don't know what is the frequency. We don't know its value. We start to search randomly. This cavity has to be designed such that the resonance frequency can be tuned. So we just tune to some place and we see the response. We don't find anything, then we change the resonance frequency of the cavity, and it gradually move it so that I'll test the next step and next step. Don't find anything, and let's move on, continuous scan. Finally, when you approach this, if it happens that it's within our search range, when we move the resonance frequency exactly on top of the action, we will see a signal and capture the photons. And once we start to leave it, the signal becomes smaller and gradually disappears. So this is how we should expect to see if there is indeed an action particle. In our current experiment, every step moves about 100 kilohertz. Takes 30 minutes to do the measurement to be sensitive enough. If we want to cover 1 gigahertz, it takes 10,000 steps. So that's about total about 1 year time. We can cover 1 gigahertz of range. I'll give you some idea of what is the order of magnitude we are talking about. We are looking at action with mass around 20 micro EV, which is 3.3 times 10 to the minus 24 joule in terms of energy. The corresponding photon frequency is 5 gigahertz. So our temperature corresponds to the quantum fluctuation, assuming there's no thermal background. Single photon due to quantum fluctuation has an energy of 240 millikelvin, corresponding noise. Therefore, we set the limit. Environmental temperature should be less than 120 millikelvin. Noise of amplifier should be also less than 120 millikelvin. This limit is posed by quantum fluctuation, so we call this kind of noise a quantum limited noise, at least half a photon fluctuation. The other implication of this number is that characteristic dimension of the cavity is about half a wavelength, that is 3 centimeter from 5 gigahertz photon. So the radius of the cavity is about 3 centimeter. In reality, we use a 2.5 centimeter cavity. So this seems to be quite difficult, but it turns out the technology already exists. This stuff are known to people who do superconducting qubits. So we learn from these people. Actually, we borrow their equipment to do this. So this is superconducting qubit system, and we replace the qubit by a cavity. Everything else was from their experiment, and that's it. It turns out it's not so difficult because they are very experienced with this kind of technology. So we were able to start doing this experiment straightforward and directly start to do the measurement. Of course, we have to build our own cavity. This is not this cavity they don't provide. So this picture shows the cryogenic system for the superconducting qubits experiment by my colleague Chen Yongfu in National Central University. This is a dilution refrigerator, which cools the temperature down to 20 millikelvin at this plate. And this is a magnet also with their system with a bore diameter of 3 inch or 7.5 centimeters. So it's good for our application. We said the characteristic dimension is about 3 centimeters. The field is about 8 Tesla. So we use this system and design a cavity ourselves. This is a cavity. Inside, it's a pure cylinder, and with a off-axis copper bar to tune the resonance frequency. You just rotate the bar to different positions, and then it limits the available space for photon conversion, and it changes the resonance frequency. So this is how we tune the resonance frequency. And with this, we can start scanning. So this is the cavity hanging under the dilution refrigerator. The cavity looks shiny. We do the experiment for 1 month, scan more than 800 steps, each step with 30 minutes. We cover a range of about 90 megahertz of range. So between 4.70750 gigahertz to 4.79815 gigahertz, about 90 megahertz range. About 1/10 of what we expect to cover eventually, corresponding to a mass of action between 19.46 to 19.84 micro eV. We set a limit. We didn't see any signal, by the way. But because we don't see any signal, we set the limit of GA gamma gamma, the coupling constant, to about 8 times 10 to the minus 14 GeV minus 1. This covers 90 megahertz, so we have excluded up to this level of the GA coupling constant. However, this limit is still about 10 times or 11 times larger than the QCD KSVZ limit. So we are not there yet. We still have a factor of 10 to improve. But if we put our experimental results together with other experiments, existing experiment, ADMX, oldest one, Haystack, they reached the QCD limit, and some experiment from Korea, CAPP. Our result is roughly at the same level as a CAPP result, and we hope that by improving our instrument, eventually we should catch up with this Haystack result in this energy range. In any case, this is the first time people have any measurement of the action in this 20 micro eV mass region. So I think time is up. Let me skip our upgrade plan, but let me just say that eventually, what we plan to have is that we will improve our experiment by having a larger volume detector, which improves the limit by a factor of 3. better amplifier, which improve our limit by another factor of 3, and stronger magnetic field, which improve by a factor of 9/8. So total improvement is a factor of 10, and this will allow us to explore SVZ benchmark model of QCD. This is our current experiment, and this is what we expect. With this improvement, we improve the sensitivity by a factor of 10, and with 1 year of data taking, we can cover 1 gigahertz of range. So I hope by 2 years from now, we were able to give an answer in this range and test the QCD action assumption. So let me come to a conclusion. On AMS side, we have searched for signature of dark matter in the cosmic ray. We see very unexpected spectrum from positron, and also, as I showed, similar feature has become visible in the spectrum of electron and antiproton. Now we are actively working on the anti-deuteron measurement. It's a low background search channel. And AMS will continue taking data up to 2030 with 4 times of acceptance. On the search for action type dark matter, we did an experiment covering a range of 90 megahertz range in frequency, and set a limit with 11 times KSVZ QCD benchmark model. Future upgrade in terms of new cavity design and new amplifier design will help us to reach the QCD limit in a 1 gigahertz band, hopefully in 2024. Yeah, that's it. Thank you very much.
Okay, thank you. Okay. Right, so I think people should be able to hear me. Right, so now is the time for questions. Any questions from the audience? So if you are looking the broadcasting, you can actually raise your question in the text box, and then I'll convey your question here in the meeting room. So for students, if you think asking a question is too difficult, oh, okay, there is one question from our faculty, Chen Junwei. He asked about can the positron, antiproton, and anti-deuteron spectra be explained by dark matter with just one mass value?
Not at this moment, no.
No.
No, sorry. This is a good question. You catch the problem with my presentation. Here, to explore dark matter, we are with anti-deuteron. We are looking at dark matter particle at about this 100 GeV energy range, while the cutoff energy we see in the positron spectrum shows that the anomaly is at the energy range of about 1 TeV or at least about 500 GeV. So there is indeed a mismatch. But on the other hand, very heavy dark matter, the peak will move towards higher energy, so it becomes less sensitive by anti-deuteron. I'm not saying that this measurement exclude each other. It's just that anti-deuteron measurement will be less sensitive to the heavy dark matter particles.
Okay, there's another question also from our faculty, Guo Guangyu. He asked, any firm evidence for axions?
No, answer is very simple. I will not stand here if I found any evidence.
You'll be winning the prize, right? Yeah.
Yeah. Also, we will not do this experiment if other people have already seen axions. But it's interesting to answer this question that we do have two candidates. You see here, the red line actually goes up here and here. We found two candidates, but we don't think they are action because, first of all, one of the candidates turns out coming from the computer. This is the Wi-Fi, the frequency of our Wi-Fi
Oh, I see.
from a computer, so it somehow gets picked up by the experiment. The other one is not clear yet, but on the other hand, this one is still there once we turn off the magnetic field. So if you turn off the magnetic field, the action conversion should stop, but the signal stays there. So we conclude that it's not from action.
All right. So any other questions, especially from students? If you feel asking the questions in English is too challenging, then you are more than welcome to speak in Mandarin if you want from the students. Oh, there's one raising a hand. Yeah, please go ahead. The R1022202. Yeah, just speak up. Yeah.
Can you hear me?
Yes.
Yes.
Thanks for the talk. So I'm wondering why your essay experiment would like to search in the match about 20 μeV. So because ADMX is searching for
very interesting question. So the answer is very simple. All this space has not been explored. Right? So from about this is about 10 micro EV, from 10 micro EV to about 1 EV or 0.1 EV. This blank region means we have no experiment setting any limit or testing this region. So any place we can do experiments is fine. You just pick what you want, and hopefully there are many people doing the experiment to cover the whole range. And so that's, first of all, there's no particular reason that we pick 20 micro EV. There is a theoretical, somehow a theoretical motivation to look around 20 or 30 micro EV range. This is because you want to have, if QCD action would have enough, if you want to create enough QCD actions that make up the density of dark matter in the universe, then 20 or, well, between 1 and 100 micro EV is what theorists think that the early universe can produce enough of action to make up the dark matter. So that's one sort of not so strong motivation for us to search for action below 100 micro EV. And now, finally, let me mention why we choose 20 micro EV. It's embarrassing to say that we choose it. We're not so clever to choose it, and then we find it. We choose this frequency just because of the ball magnet is just of that size. So that size, we have to build a cavity that can fit into the magnet, and that turns out to be about 5 gigahertz. So that's how we eventually comes up. But in any way, we chose that this is the reason we chose 20 micro EV, but 20 micro EV is not explored before, so we just do it.
Okay, there is another question from Lin Chenghan. Even though I don't know which curve he's referring to, let me just speak for him. He said, "Is there any theory model behind for the fitting curve?" So Lin Chenghan, you may want to speak up about which curve you are referring to.
Probably this curve, right? This fitting curve.
Oh, oh, right, could be. Yeah. Yes, yeah. That's the one. Yes.
Okay, so this is purely phenomenological model. So that is to say that power law is what we see in most of the cosmic ray. The cosmic ray includes proton, helium, normal matter, proton, helium, electron, etc. They all exhibit power law behavior. So we believe that in the cosmic ray, due to the propagation process and due to the acceleration process, it would naturally drive its energy distribution to a power law behavior. So that's why the energy to the gamma power. So power law is what we see in most of cosmic rays. So there's no particular reason on what shape we use to describe this extra source, the new source. But we would think that the propagation, whatever the original shape it is, the propagation process will drive it into a power law. However, if there's a cutoff, the cutoff will stay there. So we implement or introduce a cutoff term. So that's where we have this power law plus cutoff term. It's just from very simple phenomenological intuition we derive this function. On the other hand, as I said, this curve with a specific model is from a very complete theory of the cosmic ray propagation. It's derived from the actually a differential equation including all the decays, productions, and diffusion of cosmic rays in the galaxy. So this is a more sophisticated model, but nevertheless, it also fits the curve quite well. I hope this answers your question.
He says yes. Thanks a lot. Any other questions? It's very quiet on the other side here. So, any more questions for the talk today? Otherwise, not here. No. Okay, there's one more. Yeah, just speak up. The R10222002. Yeah, you can speak up.
Probably microphone was not switched on.
He's not on mute, but I don't know why he raised the hand but didn't speak. R10222002. You can speak up by yourself now. Okay, anyway, there's another question from the broadcasting room here. The question is that any collaboration with the TIDC in NS axions?
Well, no, actually, no. The technology is different. TIDC works up at this moment. TIDC is mainly developing detectors based on silicon detector, But as you can see, we actually borrow the equipment from people doing superconducting qubits experiment. So the technology is quite different at this moment. There's always some opportunity to collaboration, but it's not the case at this moment.
Right.
I myself is involved in TIDC, of course, for other reasons.
Right. He replied saying that they also developed SNSPDS. So I think he's working on something similar.
I think it refers to a low temperature photon detector. It's probably I don't know the detail, but my understanding is based on silicon technology. Here we're talking about different frequency range. We're talking about microwave photons, so it's extremely low. The technology you refer to in GIDC is probably at the visible light frequency. Yeah.
Okay, and there is another question from again our faculty Chen Junwei. He asked, can a good measurement at 1 TeV positron spectrum differentiate dark matter and actual interpretations? Because you said for dark matter case, it should go back to the power law background.
Yeah, it depends on how you model it. People, of course, some people claim that pulsar's contribution, if this is coming from pulsar, it may also have this kind of cutoff behavior. But there are also other models saying that it's not, because pulsar can have, we may have many pulsar with different energy scale, so it will not be such a sharp drop. It probably is more smooth if it involves many pulsars from different with different energy scale, and that's the problem. With dark matter, there's a unique source with a single cutoff behavior. We think that this should provide some good information to differentiate these two models.
Okay. So any more questions? If not, then let's call it a good day. So thank you again, for a great talk. It's very interesting, and especially in the conclusion, we see some further more exciting, experiments. The expansion of current scale coming along pretty soon in about 2 years time. So so maybe we should invite you back in 2 years time to share about news. And I'm sure it will be very interesting and very exciting to learn all the current developments. And I received a bunch of feedback from the broadcasting room saying this is really a very exciting moment and a very excellent talk. And thank you so much.
Thank you very much.
Thank you. All right. Bye-bye.
Bye-bye. Thank you.
And for the students, you probably need to stay for another while because the TA has something to say. And 张教授就非常谢谢你，对，今天真的很不好意思，就变成线上了。这个
谢谢啊，我不知道怎么离开这个啊。Let me try
就是右下角有一个下方最右边那个按键是挂断。哦，离开你箭头移到最上面。
对啊。